The internet is not a thing, it's a system of systems. At its core, it's just data moving between computers. Not magic, not the cloud, just machines sending and receiving information. Everything you do online, loading a page, sending a message, watching a video, is data being transferred from one computer to another. That's it. But how that actually happens is where things get interesting.
Because that data is never sent as one piece. It's broken into smaller chunks called packets. Each packet contains a piece of the data, the destination address, information about where it came from. Think of it like sending a long message as hundreds of tiny envelopes instead of one big package. Why? Because smaller pieces are easier to route, recover, and manage. If one packet gets lost, only that piece needs to be resent, not the entire message. Once created, those packets begin their journey. And they don't travel in a straight line. They move through a network of routers. Routers are decision makers. Their job is simple. Look at a packet, check its destination, send it in the best direction. But here's the key. There is no single fixed path across the internet. Packets from the same request can take completely different routes and still arrive at the same destination. Some might go through London. Others might pass through Frankfurt. Another might reroute through New York, all for the same web page. That's why the internet is resilient. If one path fails, traffic is automatically redirected. No central control. No single point of failure. Just constant adjustment. Behind these routers are networks. And those networks are owned by different organizations. Internet service providers connect your home to the wider internet. Companies run massive data center networks. Governments maintain infrastructure. And all of these networks interconnect. They form agreements to exchange traffic. This is called peering.
Instead of one giant network, the internet is thousands of smaller networks stitched together. That's why it's called a network of networks. Now, before your data even reaches a router, something else happens. You type a website into your browser. Let's say you type in a domain name. But computers don't understand names. They use IP addresses. So your device asks a system called DNS, Domain Name System.
DNS is like the internet's phone book. You ask, what is the address of this website? DNS replies, here's the IP address. Only then can your request begin its journey. That request travels outward, from your device, to your local router, to your ISP, into the wider internet. Eventually it reaches a server. A server is just another computer, usually a powerful one, sitting in a data center somewhere. That server receives your request, processes it, and sends data back. Again, not as one piece, but as packets. Those packets travel back through the network, reassembled by your device, displayed as a web page, video, or message. All of this happens in milliseconds. Now zoom out. Underneath everything is physical infrastructure. The internet is not wireless at its core. It runs on cables, fiber-optic cables specifically. These cables carry data as pulses of light, not electricity, light. That's how information moves so fast across continents. There are cables under the oceans, massive submarine cables connecting countries, carrying nearly all international internet traffic. Satellites exist, but they're not the main system. They're slower and used in specific cases. Most of the internet is underground or underwater, hidden, but essential.
On top of that, the physical layer is a set of rules. These rules are called protocols. Protocols define how data is formatted, sent, and received. Without them, nothing would work. The most important ones are IP, Internet Protocol, TCP, Transmission Control Protocol, HTTP, Transfer Protocol. IP handles addressing. It ensures packets know where to go. TCP ensures reliability. It tracks packets, reorders them. Requests are missing, so the data arrives complete. HTTP is what your browser uses to request web pages. Together, they form the foundation of communication online. Now, here's something most people don't realize. Speed on the internet isn't just about bandwidth. It's about distance and routing.
The further the data has to travel, the longer it takes. Even at the speed of light, distance matters. Routing efficiency matters too. A poorly routed path can slow everything down. That's why companies invest heavily in infrastructure. They want data to travel faster and more directly. Another key concept is caching. Not every request goes all the way to the original server. Sometimes, copies of data are stored closer to you. This is done through CDNs, content delivery networks. They place servers around the world. So when you load a website, you're often getting data from a nearby location, not the source. This reduces latency, speeds things up, makes the internet feel instant. Now think about scale. Billions of devices, trillions of requests, all happening simultaneously. And yet, it works because the system is decentralized. No single authority controls the entire internet. Different organizations manage different parts. Standards are agreed upon, but control is distributed. That's what makes it powerful and fragile in a different way. Because coordination matters. If major networks fail to cooperate, parts of the internet can become unreachable. Now let's talk about security.
Data traveling across the internet is not automatically private. Packets move through multiple networks. Any point along the way could theoretically inspect them. That's why encryption exists. Protocols like HTTPS encrypt data, so even if intercepted, it can't be easily read. Your browser and the server establish a secure connection. They exchange keys, then encrypt everything that follows.
This is what protects passwords, messages, and sensitive data. Without encryption, the internet would be unsafe to use. Another layer is addressing. Every device connected to the internet has an IP address. This is how it's identified. There are two main versions: IPv4, IPv6. IPv4 is older and limited. IPv6 was created to support more devices because the internet keeps growing. Phones, laptops, servers, smart devices, everything connects. And everything needs an address. Now consider reliability again. When you load a web page, your browser doesn't just make one request. It makes many. For images, for scripts, for styles. Each one is a separate request. Each one sends packets. Each one receives responses. All coordinated in real time. If something fails, retries happen automatically. You rarely notice because the system is designed to recover. That's the core idea. Resilience through redundancy. Multiple paths, multiple systems, constant fallback. That's why the internet doesn't break easily. It bends, reroutes, adapts. Now zoom in again. When you click something, a chain reaction starts. DENS lookup, connection established, request sent, response returned, content rendered, all in fractions of a second. It feels instant, but it's not simple. It's layered. Each layer handles a specific job: physical transmission, routing, reliability, application logic, stacked together, working as one system. That's the internet. Not a place, not a cloud. A process, a continuous exchange of data across a global mesh. Every message you send, every video you watch, every page you load, it's all packets, moving, routing, reassembling.
Across cables, servers, and networks, in real time, at a massive scale. And the reason it works so well is not because it's simple, but because it's modular. Each part does one job and does it reliably. That's what allows the whole system to function and grow and adapt.
So when you think about the internet, don't think of it as something you go on. Think of it as something that happens constantly, everywhere. A global communication mesh built on packets, protocols, and physical infrastructure, quietly powering almost everything you do. If you never looked at the internet the same way again, hit like, subscribe, and tell me what surprised you most.